Commercial and general aviation aircraft are engineered to operate for decades. Over a 40-year lifespan, the physical components of that machine are completely cycled out. Engines are overhauled, avionics are upgraded, and structural brackets are swapped. This creates a profound regulatory challenge. If the aircraft flying today is no longer strictly the machine built by its original manufacturer, how do aviation authorities guarantee its safety? Aviation safety relies on a strict, hierarchical architecture of intellectual property and regulatory approvals that governs every physical repair and modification. This diagram illustrates the core rule of aviation certification. Every bolt, bracket, and screen on a modern aircraft must legally trace back to a single origin point of approval. This certification dependency tree prevents unauthorized, unproven probes from entering the aviation ecosystem. To understand how this ecosystem operates, we have to build this legal architecture from first principles, starting with the naked airframe. Understanding this specific dependency tree is the only way an engineer or mechanic can legally keep a modified aircraft in the sky. This animated wireframe represents the starting point of any new aircraft. This is the Type Certificate, or TC. It's the original recipe issued to major manufacturers like Boeing or Airbus. The TC covers the airframe, engines, and propellers as a single proven design. This document is heavily guarded intellectual property. It proves the physics, the aerodynamics, and the safety of the manufacturer's specific geometry. Without a type certificate, an aircraft model legally does not exist. It serves as the immutable bedrock for all future modifications. While the type certificate approves the abstract model, the reality changes when a physical aircraft rolls off the assembly line. That individual aircraft requires a pilot's operating handbook, or POH, which functions as its specific owner's manual. This document is legally required to be physically on board during flight, and it is tied directly to one individual tail number. Because of minor variations in manufacturing, the POH contains unique data that the broader TC cannot cover, such as the exact weight and balance calculations of that specific airframe. The distinction is clear. The TC proves the design is safe to build, while the POH ensures the individual physical plane is flown safely. Consider an engineering scenario where a third-party company wants to add a new exterior camera mount or aerodynamic winglets to our pristine aircraft. To do this, they must acquire a Supplemental Type Certificate, or STC. This is the required regulatory document for any major change to a previously certified design. An engineer cannot get an STC without an original type certificate. The modification is strictly tethered to the base design. The applicant must prove this modification doesn't compromise the baseline safety metrics established by the original TC. Beyond the engineering requirements, STCs carry strict financial realities. They are highly valuable, tradable intellectual property. Owning an STC grants exclusive rights. Anyone else wanting to install that specific camera mount must purchase the right to use your STC. STCs allow widespread commercial innovation in aviation without ever forcing the original manufacturers to constantly redesign and test their entire base aircraft. If a major modification requires an STC, standard maintenance requires a different pathway. Consider a standard structural bracket on the landing gear that wears out and requires replacement. This replacement is governed by a Parts Manufacturer Approval, or PMA. It is the regulatory authorization to manufacture replacement parts. While an STC changes the design, a PMA is used to legally replace what's already there. It operates like the difference between generic and name-brand pharmaceuticals. A third-party PMA bracket must be proven just as safe and structurally sound as the original equipment manufacturer's bracket. PMAs break original manufacturer monopolies on replacement parts, significantly lowering maintenance costs for operators. In European jurisdictions overseen by EASA, you will see the European Part Approval, or EPA, which serves the exact same regulatory function. PMAs and EPAs ensure the physical integrity of aging aircraft by maintaining a competitive, highly regulated supply chain for replacement hardware. Structural brackets are specific to a single airframe, but the industry also relies on universal appliances used across fleets, like tires, seatbelts, or GPS units. These components are regulated by the Technical Standard Order, or TSO, which establishes a minimum performance standard for specified materials and appliances. This diagram shows the unique mechanism of a TSO. It certifies the part itself in isolation, completely independent of any specific airplane model. A TSO-certified part is considered pre-approved to meet baseline safety and environmental standards. Installing a TSO-certified GPS makes securing an STC much easier because the engineer only has to prove the physical installation into the dashboard is safe, not the inner workings of the GPS itself. TSOs modularize safety, allowing specialized tech companies to build universal components that can be legally integrated across the entire aviation industry. Occasionally, regulators identify a critical flaw in an active fleet. The FAA will issue an Airworthiness Directive, or AD. This is a legally binding, mandatory order to fix a specific problem before further flight. This creates an engineering dilemma. What happens to an operator when the FAA's official fix is prohibitively expensive, or the mandated parts are out of stock globally? The regulatory solution to this gridlock is the Alternative Method of Compliance, or AMOC. An AMOC allows an engineer to resolve the Airworthiness Directive's problem using a completely different method than the FAA originally mandated. The engineer must mathematically and structurally prove to the FAA that their alternative repair achieves the exact same safety standard as the original directive. AMOCs provide critical operational flexibility, ensuring that entire fleets aren't permanently grounded by supply chain failures or rigid bureaucracy. Looking at this complete animated wireframe, we see how all these documents interact on a modern operational aircraft. A modern operational aircraft functions as an interlocking ecosystem of localized approvals. This structure combines the manufacturer's original design with decades of third-party innovation and specialized hardware. The TC, STC, PMA, TSO, and AMOC provide strictly mapped engineering pathways that maintain the integrity of the airframe. By requiring every single change to mathematically map back to the original recipe or meet an independent standard, authorities can decentralize innovation without ever compromising the structural integrity of the airframe.